Hello everyone. It's been a while since we've last done a video on. Um, it's been a while since we've done this kind of videos. It was vacation here and had some family matters I had to attend to. Anyways, without any those details aside, let's continuation to what we've been working on as of late. We've covered a pretty decent chunk of information. Um, we started off linear algebra from scratch. We started off with numbers, and then we went on to sets, and then we um, we studied a bit of equivalence and functions, and then we moved on to the slopes. Then we moved on to the slopes, and then we studied a bit of linear equations, and we moved on. We also studied a bit of parabola, and then we went on with solving linear equations, and we done the linear equation systems, as well as you've seen how to solve those using matrices, matrix, and we've also studied matrix. So these few videos, this video and the upcoming ones would cover, will basically review what we've studied so far and try to, recall what we've studied. Moving on to the practical part after this, we will try to implement a bit of the theory that we've studied using code and publish it for everyone's sake. Or for everyone to actually benefit from it, right? Anyway, so without any further ado, let's begin. So with the numbers, what's the deal with the numbers? We've studied the numbers, and we know positive numbers exclude the zero. We have the prime numbers. Prime numbers do not include the one, and they must be positive, and one is not really a prime number. Okay. Rational numbers, natural numbers, we already know what the natural numbers are. Real numbers, though, is real numbers is natural numbers is a subset of real numbers. Okay. Irrational numbers that cannot take a fractional form. So whole numbers can include negatives and zeros. Okay. Prime numbers must be positive. 1 is not a prime number. Or we could do, and 1 is not a prime number. The positive proper factors of an integer include 1 and the number itself. Where the denominator, you have the denominator and the denominator. The denominator is actually larger than the numerator. That's what a proper fraction is. So we have this set of information that's, I don't think this is properly said here. This has to move to another place. It has to. This has to come here. I think we should move all of this. Sorry. Should move all of these to functions. I believe that's the deal. Right, so if we go to functions, we should be able to arrange everything over there. My connection is a bit lousy, so bear with me. Where I am now, they have this thing where they meter the tethering, and I should look for a resource where I can bypass this limitation on tethering, because on my phone everything works like super fast, but the moment I start tethering, things like drop drop. So these should move to the top like right about here. Okay, that's that. I'll have to. Okay, so let's um, try to, before we do the functions, we let's go to the sets. So sets, to quickly recap without going through these notes. So we know that a set can have multiple subsets, and by default, any set has two subsets. So the set itself is a subset, and the empty set is also a subset of the main set. So when you have a union, it means the result of both these elements. And if you have an intersection, so it's only those elements that exist in A and B, but do not exist in. So it's only those elements that exist in A and B. Um, and a proper subset. Okay, so we have a subset is basically a number of elements that are part of the group of elements that exist in the original set. And a proper subset is when A is a subset in B, and there is an element in B that is not in A. If the same elements in A exist in B and vice versa, this will make identical sets and can be considered subsets, as we can see. So a proper subset is when you have an element that's not and it's not part of the subset. And then when you have a union, A is a subset of B. A is a subset of B. So this symbol here indicates that it's a subset. The empty set is a subset of every set, including the empty set itself. Every single element of empty is also an element of X. Or can you name an element of empty that is not an element of X? Yeah, okay. When we say ordered in sets, means the size, the number of elements in a set, and you can get that using 2 to the power of n. That's when you get the number of subsets. To get the proper subsets to the power of n minus 1, or subsets, you can has infinite order. Okay, it's the number of elements. We should not confuse the number of elements and the should not confuse the number of elements in a set and okay, so we can get the number of subsets using Pascal's triangle. It might look like it's it's a nice way to. It's an interesting concept to use, the Pascal's triangle, but I don't think it's really practical because you'll have to have the triangle drawn, and every time it's just a nice phenomena that you can actually use the Pascal's triangle for multiple computations or for multiple sets of computations. And there's an actual formula to tell the number of elements, the subsets for taking, say, the notation n choose k can be written n factorial over k factorial minus n minus k. Okay, so the number of combinations working out the value at any place in Pascal's triangle. Capital letters represent the set. The lower letters represent an element in that set. Union is like the or, intersection is like the end. Subtract soccer minus tennis. Those who play soccer but not tennis. Universal set is a set that contains everything in other sets of interest. Notice the symbol. Symbol is capital U and is easy to confuse with the traditional uni symbol. Complement. Everything that's not. Okay, an index set is a set whose members of another set. For instance, if the elements of set A may be indexed or labeled by means of elements of set J, then J is an index set. Okay. The interval 2 to 4 includes such numbers, a lot more. In interval notation, we just write the beginning and ending. Yeah, the way basically you write. So this is 20 means it's included in the number of elements in the set. 0 in this case is not included. Yeah, this means it includes and this means it doesn't include. So we could actually use there's a union B, all the elements in A plus all the elements in B, right? So it's an addition. It's an addition, but you'll have the duplicates. So you just remove all the elements minus the intersecting elements so that you remove the duplicates from that. The cardinal number of the union of two finite sets is the cardinal number of the size, the order. Number of elements in A plus number of elements in B minus their intersection. And the intersection, you would subtract the union. Set A contains 35 elements and set B contains 22 elements. There are 40 elements in A union B. And how many elements are in A intersecting B? So A is 35, the other one is 22. So this plus this minus 40, 17. So we have a commutative property and associative property. Commutative property means you can add a B or B plus A, it doesn't really matter. But associative property, you can add A plus B, it would be the same, and then add C. Or you can add A plus C and then you just add the B. That's associative property. Symmetric difference. Symmetric difference. This was the interesting bit. This is the interesting part. So you would you have A has 1, 2, 3, and then B has 1, 4, 5. So A minus B, you would be left with 2, um, 2 and 3. B minus A, you would be left with 4 and 5. Symmetric difference commutative, so A delta B is like B delta A. Yeah, which would equal to 2, 3, 4, 5. Based on the text, symmetric difference is the new union excluding the intersection, or the elements that exist in either sets but not in both. So the union minus, so A minus B union B minus A union B minus A intersecting B. Right, nice. So this is the first part of the review. We've done the sets, the next we'll do these two. We should look for sources where we can do the above using code. I'll look for some.